Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics courses, please consider subscribing, checking out some videos, but let's go ahead and get into the current one. I want to take a look at describing a basis for a topology, and the idea for a basis is the following. If I have, let's say, an infinite set or even a large finite set, sometimes it's not really practical to list all of the open sets. For example, let's say I give you the set X consists of 1, 2, 3, 4, and I can define a topology on this. Let's say the empty set X itself, 1, 2, and then 1, 2. Okay, so this would be a topology on that set. But this is a finite set, and in fact, not only is it finite, but there's 4 elements, right? If this set had 1,000 elements, or was even, say, infinite, it's not really practical to just list all of the open sets. And so the idea for a basis is it gives me a much simpler list to generate the topology. Just like for, say, in a vector space, we have, say it's like a 3-dimensional vector space, 3 vectors, 3 linearly independent vectors generate the whole space, right? So we have this smaller list that we then use to create everything else. And so here is the definition for a basis for a topology. So definition. Okay. A basis for a topology, tau, on a set X is a collection of sets, usually written as script B. So a basis for a topology is a collection of sets B for which the following holds. For every open set in tau, so for every open set, there exists a collection of elements in B. So there exists, let's say, Bi indexed by the set I, which is a subcollection of B. So in other words, I can take some elements of this basis. So for every open set, there's a collection of basis elements such that U is the union of those basis elements. So by taking unions of basis elements, I can create any open set. Okay? And what this does, this allows me to describe a significantly smaller collection of sets, and that we can then generate the whole topology rather than just listing the whole topology. So for example, all right, so let's take the real numbers with the basis for a topology consisting of the following. I'm going to take the following collection. B is the set of open intervals A to B, where, again, A is just going to be strictly less than B. And this right here forms a basis for the usual topology, because in the usual topology, open intervals are open, and therefore unions of those are open. And so this right here takes all the possible open intervals, individually open in single intervals, and then unions of those creates everything in, again, like I said, the usual topology. Another example. Let's say X is any non-empty set. Okay, so X is any non-empty set. Then let's say I'm going to take the collection B, which consists of the following. I'm going to take all singletons where A is an element of X. So every single singleton element in the set X is an element of this basis. What does that generate? Well, this generates the discrete topology. Remember that the discrete topology was the topology in which every single, actually it didn't show up real well there. The discrete topology was the topology in which every single set is open. And so if I take the collection, the base is consisting of all singletons, and I can generate any possible subset of X by just taking unions of singletons. Okay? Let's take a look at an example in R2. See if that's showing up okay. All right. So let's consider R2 with the usual topology, and let's see if we can visually come up with some basis sets for this. So let's say I have the following open set. And so it's actually, I'm going to do this two different ways. All right, and let's say I've got the same set U, which is open in the usual topology, and what could I use for basis elements of this? Well, on the one hand, I could take, let's see what color I want to use here. I could take a point here, and I could take open disks around it. And of course, open disks of different sizes. So I could take, large ones and small ones and so on and so forth, but I could take just the union of all possible open disks that would then create this entire open set. I also could say, all right, well, if I take that same point, I could take an open square of different sizes, and I could also generate the same open set U. Therefore, we could have, for my basis, we could have open disks would be one basis that we could generate or use to generate the usual topology. And over here, we could see that we could also use, say, open squares to generate the usual topology. But at any rate, the concept is that it allows me to specify either a smaller number of sets, or I can, in the case of like the usual topology on the real line, just say all open intervals, I can generate a list more systematically, which would then kind of give me more of a feel for how to build up the topology itself, and it's not so overwhelming where I just kind of say, well, it's a whole bunch of these different sets, or I have an infinite number of sets that we can't really specify very clearly. But at any rate, thank you for watching. Please consider subscribing.